Hello, everyone. Today we're going to go to the last section of stoichiometry, which is the yield aspect of things. My next door neighbors are playing music kind of loud, so if you hear music in the background, that's where it's coming from. So my apologies in advance if that does happen. So yield in general. So the word yield, if you see this, there's different types of contexts that you can use it in. You know, if you're thinking of a traffic sign, yield means to slow down or to stop. But in this case, yield is referring to how much of something you get. So like, this is my yield. This means this is how much of something I got out of something else. So like out of a project or out of something, this is my yield. This is what I got from it. So that's what yield is. And there are three types of yield that we will be looking at. So there's theoretical yield. Theoretical yield is what you're supposed to get if everything goes perfectly. If everything goes 100% according to plan, this is how much we should get. That's theoretical yield. Okay. Actual yield, as the name implies, is what you actually get. Okay. So then this you have to get from just the experiment. Whatever you do, you measure out how much of something you got. That is your actual yield. So theoretical is what you're supposed to get. Actual is what you actually got, and then percent yield is just your actual divided by theoretical. Okay, so what you were supposed to get, okay, so actual, what you were supposed to get divided by, I'm sorry, what you did get divided by what you were supposed to get. Okay, so this is percent yield right here. Okay, it's going to come out to be a percentage. It's what you actually got divided by what you were supposed to get. Okay. And this number is always going to be less than, in theory, less than one, because there's no such thing as a perfect reaction. And you can't get more than what you were supposed to get. That's impossible. If you think about it from a recipe perspective, you can't accidentally make more of a food if you are limited on the amount of ingredients that you have. You know, you can't accidentally make more of something. That can't happen. So this number has a maximum. It can only be a maximum of one, because anything divided by itself is going to be one. That's the highest it can get, and then the decimals or the percentages afterwards. So it's actual divided by what you were supposed to get. That is your percentage. How do you find this? In order to find the theoretical yield, you need to know how to find the limiting reactant, okay? Because the limiting reactant is what's going to control or dictate how much product you can make, okay? Think about it like this. So a common equation we were looking at all the time, let's look at the water. Okay, let's make water. Water from oxygen and hydrogen, okay? So this is our chemical reaction that I'm going to use to explain this real quick. H2 plus O2 makes H2O. Okay, so this needs a 2 here and a 2 here, and now it's balanced. Okay, so let's say I want to make water from hydrogen and oxygen. And let's say I have an infinite amount of oxygen. I have an infinite amount. I will never run out of oxygen. But I only have, let's say, 10 moles of hydrogen. Since I only have a limited amount of hydrogen, hydrogen is what's going to control how much water I can make, because I'm going to run out of hydrogen first. So what I could theoretically get has to be based on which ingredient I'm going to run out of first. I'm going to run out of hydrogen first, so I need to do my calculations based off of hydrogen. Okay? That is how you calculate theoretical yield, and we'll go through an example now. So step one is figuring out the limiting reactant. And if you remember from yesterday, you do that by dividing the number of moles of an ingredient that you have by the coefficient. Okay. So the first thing they do here is, I always tell you, if everything is not in moles, convert everything to moles first. So we have 27 grams of aluminum and we have 71 grams of chlorine, and this is our chemical equation. Okay, this is our chemical equation. For every 2 aluminums, you need 3 chlorines. Okay, so this is what the recipe is telling us. Convert our gram amounts to mole amounts. So we have 1 mole of aluminum. We have 1 mole of aluminum. And we end up having 1 mole of chlorine. So we have 1 mole of both. We have 1 mole of aluminum, 1 mole of chlorine. Okay, cool. Now we have to divide those numbers by the coefficient to see which one is limiting. So this one's going to get divided by 2 because there's a 2 in front of the aluminum, and we're going to get 0.5. And then this one is going to get divided by 3 because that's the number in front of the chlorine, and you're going to get 0.33. The one that's limiting is the one that has the smaller number. 0.33 is smaller than 0.5, so now we know chlorine is our limiting reactant. Chlorine is what's going to control how much product we can make, okay? So now that we know which one is the limiting reactant, now we can start to figure out what is our theoretical yield. What is the maximum amount of product that we can make with this amount of chlorine that we have? This part is just a conversion. So now we need to convert moles of chlorine into moles of aluminum chloride. This is where you got to set up your ratio like we did in the past, okay? So look at the recipe. What the recipe says, for every 3 chlorines, we will get 2 aluminum chlorides. That's what this says. For every 3 chlorines, we will get 2 aluminum chlorides. So then you're going to set up your ratio based on these numbers, okay? And that's what they do here. This piece right here, this is your ratio. Remember, what you are converting to goes on top. We want to know how much aluminum chloride we're going to make. We know how much chlorine we have. We want to know how much aluminum chloride that's going to make. So aluminum chloride goes up top, okay? And then what you are converting from goes on the bottom. So we're going from chlorine to aluminum chloride. Okay, so that's why it's set up the way it is. And then these numbers, the 2 and the 3, come from the chemical equation. So the 2 is what's in front of the aluminum chloride, and the 3 is in front of the chlorine. So that's how the ratio is set up. So now that you have your fraction set up, now you multiply it out. We have 1 mole of chlorine, multiply that by 2/3, and you will get your moles of aluminum chloride, okay? So this piece right here, this part is us converting moles of chlorine into moles of aluminum chloride, and you get 2/3, okay? So 0.67, that's the decimal form, okay? So this part right here is 0.67. This is moles of aluminum chloride, okay? Now that we have this number, the next step, it wants us to convert it into grams. We want to know how much aluminum chloride we're going to make, but in grams, okay? So then this step right here is us converting moles to grams, okay? So again, what you are converting to goes up top. We are converting to grams, so grams should be up top. We are coming from moles, so moles should be on the bottom. And then the 133 comes from the atomic masses that you add up. So chlorine is 35.45, and then aluminum is 26.98. You add them up. You have 3 chlorines, so you got to triple the chlorine number, and then you add the aluminum, and that's where you get your 133. So that's where this number came from. And you multiply everything out, and you get 87.8 grams. This right here is our final answer. That is our theoretical yield. So if this reaction goes perfectly, no hitches, we get a 100% conversion, we will get 87.8 grams. Okay, this is our theoretical yield. It's what we're supposed to get if everything goes perfectly. Okay, but then we know there is no perfect reaction. Okay, there is no perfect thing. Okay, nothing in science is ever exact. Okay, a lot of things are estimations. Okay, so now we got to get into calculating those efficiencies. Okay, so now we got to look at the percent yield. Percent yield, again, it's what you actually got divided by what you were supposed to get. So in this case, we were supposed to get 87.8. So on the bottom, you would put 87.8. And then if we were able to measure what we actually got, that's what we would put up top. Okay. So now let's do an example where we calculate the percentage. So here we want to calculate percent yield. Boom. So we have a combustion reaction. We have methane with oxygen making carbon dioxide and water. This is a combustion reaction. We have 24 grams of methane Again, methane is CH4, and I'll label that for you so you don't forget. Methane is CH4. We have 24 grams of it, and we have 30 liters of oxygen. So we're given mass in one and volume in another. So we got to convert them both to moles. And it tells us how much carbon dioxide we make. We make 12.1 liters of carbon dioxide. That's our product. So they give us our initial ingredients and they tell us how much we make. We want to calculate the percent yield. So to calculate the percent yield, we need to first figure out how much are we supposed to get. So we have to find the theoretical yield. So step one is finding the limiting reactant. Because remember, theoretical yield is based off of the limiting reactant. So we need to find that first. Okay, so convert everything to moles first. So remember, to go from grams to moles, you need to divide by the molar mass. So this would be 24 divided by the molar mass of methane. Carbon is 12, hydrogen is 1. We have 4 of them, so that's 16. Okay, so that's 24 divided by 16, which gives us 1.5. So we have 1.5 moles of methane. Okay, that's what this is. We have 1.5 moles of that. And then to go from volume to moles, you have to divide by the volume at STP. Okay, remember we are at STP. And that's 22.4. Okay, so again, this is my volume divided by the volume at STP, which is 22.4. Remember, that's from the mole unit. And if you do that, we get, I'm going to round this, 1.34. Okay. Okay. So let me get some space. So this is 1.5. And this is 1.34. That's moles, okay? I'm going to look at this later because this is how much we actually got. These numbers right here are how much we started with. So right now we're just trying to figure out how much we're supposed to get, okay? So I'm going to save this number for later, the 12.1. Okay. So now that we know how many moles of each we have, now we got to figure out which one is limiting. So the coefficient in front of the methane is 1, the coefficient for the oxygen is 2. So then we would do 1.5 divided by 1, which is going to be 1.5. I think right away you can see which one's going to be limiting. And then you would do 1.34 divided by 2, which comes out to be 0.67. So oxygen is our limiting reactant. That is what's going to limit how much of the products we can make. Okay. Now that we have our limiting reactant, now we do the conversion to the product. Okay. So we were looking at carbon dioxide, so we need to convert this into carbon dioxide. So step one, I always tell you, is to set up your ratio. We are going to carbon dioxide, so carbon dioxide should go up top. We are coming from oxygen, so oxygen should go on the bottom. Then we look at the coefficients. Carbon dioxide gets a 1, and oxygen gets a 2. Okay, and then step 2 is to just multiply it out. So we have 1.34 moles of oxygen. That needs to get multiplied by 1/2, which is going to come out to be 0.67. So theoretically, we are supposed to get 0.67. This is moles of CO2. Okay. This is what we're supposed to get. Okay, 0.67 moles of CO2. That's what we are supposed to get. Okay, and give me some more space here. Okay, 0.67. We are almost done. Now that we know how much carbon dioxide we're supposed to get, let's look at the problem again. It gives us carbon dioxide in volume. So in order for me to compare this, I need to convert this 0.67 moles into liters. Okay, so to do that, 0.67, this is in moles. I need to convert this to liters. So then this is going to be multiplied by times. So I want to go from moles to volume. So since I'm going to volume, liters should go up top, moles should go on the bottom. And then we know that in 1 mole, it's 22.4. Multiply that out. And we get 15.01 if you round it. So this is how much carbon dioxide we were supposed to get. If everything went perfectly, we would get this much carbon dioxide. The problem tells us we only make 12.1. So to answer the question, what is the percent yield? We take what we actually got, which is 12.1, and we divide it by what we were supposed to get, which is 15.01. And you get your final answer is divided by 15.1. We get 0.806, which is the same as, if you convert that to percentage, it is 80.6%. That is our percent yield, okay? Out of what we were supposed to get, we only got 80% of what we were supposed to get, okay? So now I'm going to go through. Now they have everything we just did here. So now let's go through it to check our work, okay? We just did this ourselves. They have the work here. Let's double check to make sure we did everything correctly, okay? Step 1, convert everything to moles, 1.5 and 1.33. Good, we did that. Step 2, figure out which one is limiting. They divided by the coefficients. They did that. They found out that oxygen is limiting. We did that as well. Now we're on track. Then after you find out which one is limiting, you need to convert that into the other chemical that we're looking at, the product. So they convert moles of oxygen to moles of CO. That's what this piece is right here. This is going from moles of oxygen to moles of carbon dioxide. Okay, and then after they convert it to moles, they then convert it into liters. Okay, they convert it into liters. And then after they get that, they divide everything out and they get their final answer. They got 80.7. We got 80.6. But the reason we got 80.6 is because I used 15.01. They just rounded down to 15. Okay. So they did exactly what we did. Okay. So everything we did matched up. How are we doing on time? Okay. We're at the 20-minute mark. Okay. So I believe this should be the end. No, there's one more piece. Okay. Calculating excess. All right. So this is finding percent yield. I'm now going to jump to calculating excess. So all calculating excess means is just figuring out what's left over. How much is left over? That's what calculating excess means. So once you know how much of something you're going to use up, you know the other. If one is limiting, the other one has to be in excess. Okay? That's what this is saying. So in order to do this, you need to figure out which one is limiting and then subtract the amount that you use up from the initial, okay? So for example, let's say we have, again with the water example here, the exact same example. So we have the water example. We're making water from hydrogen and oxygen. We have 6 grams of hydrogen and 160 grams of oxygen. How much of the excess will remain? So notice how they don't tell us to find yield or anything like that. With these types of problems, you assume the reaction goes perfect. So again, you are assuming perfect conditions, okay? Assume that everything goes perfectly, everything is used up. How much will you have left over if everything goes perfect? Okay, that's what they're asking. So step 1 is always convert everything to moles. We have 6 grams of hydrogen. 6 grams of hydrogen gas is equal to 3 moles, because remember the molar mass of hydrogen is 2 because it's H2. So we have 3 moles of this. I know that right away. We have 3 moles of this, and then 160, divide that by 32 because that's the molar mass of oxygen. I'm trying to speed this up a little bit, and this comes out to be 5. So we have 5 moles of oxygen gas, and we have 3 moles of hydrogen. Now we need to figure out which one is limiting. Right away, I can see it's going to be hydrogen because you have 3 divided by 2, and then you have 5 divided by 1. Okay, this is going to be 5. This is going to be 1.5. So this is limiting. Okay, I'm going to highlight it in red. The red thing is limiting. This is our limiting reactant. So if this is limiting, we know that oxygen is going to be in excess. Okay, so if we use up all 3 moles of hydrogen, how much oxygen are we going to use up? So now let's pretend we don't know how much oxygen we have. Let's pretend we don't. Okay, we know we have 5 moles, but we got to base it off of the limiting. So we have 3 moles of hydrogen. How much oxygen do we need to exactly use up those 3 moles? This is where you set up your ratio. So we have 3 moles of H2. We need to convert that to moles of oxygen. We're going to oxygen, so oxygen goes up top. We're coming from hydrogen, so hydrogen goes on the bottom. Put in the coefficients, 1, 2. Multiply everything out. Hydrogen cancels, and you're left with just oxygen, and you're going to get 1.5 moles of oxygen. So what this means is that to use up all 3 of these moles, we only need 1.5 moles of oxygen. So this is how much oxygen we are going to use up. Okay, we're going to use up that much. Okay, but we know how much of oxygen do we have? We have 5 moles of oxygen. Okay, that came from here. 160 divided that by 32, you get 5. So now I'll put the 5 back. We have 5 moles of oxygen. We only use up 1.5. So then at the end, we're going to have 3.5 moles of oxygen. This is how much excess we will have at the end. If everything goes perfectly, that's how much oxygen we're going to have. Okay? So again, let's go through the work. Step 1, they convert everything to moles like we did. Step 2, find which one is limiting. They found out that hydrogen is the one that limits. Step 3 is find out how much oxygen you're going to use up based on the limiting. Okay, hydrogen is limiting, you have to convert it. They do the calculation, they get 1.5, just like us. And then all you do is subtract how much oxygen you started with how much you use up, and then you can figure out how much you'll have left over. Okay? So today, you're going to be doing class set 4, and you will be doing everything pertaining to the previous class sets and now the addition of the excess and limiting and the percent yields. Okay? So in number 1, you do not have to do E. Okay, E, ooh, I missed the mark completely on that. Okay, you do not have to do E. E is talking about geometry, which we've already done in the previous unit. I don't want to focus on that anymore. Okay, and then if you look at 2, Part D also focuses on something that we've already discussed. I don't want to spend time on that anymore. Okay. So in number 1, skip E, and number 2, skip D. Okay. What's new now is now you can do the percent yield. Okay. Now you can do the percent yield calculation. So there will be some cases where you're given the percent yield and you have to work backwards, and there's other cases where you might have to find the percent yield. Okay. So if you look at number 1, part C, it says nitrogen dioxide is produced at 86% yield. So they tell you what the percent yield is already. And then they ask you how many liters of oxygen would be needed to react at, this is STP, okay? All this is just STP. So 1 atmosphere and 273 Kelvin, that's at STP, okay? So you need to base this question off of the previous ones. Everything builds, okay? So if you read through the problem, they don't give you gram amounts in here. What they give you is gram amounts in part B, okay? So give me one moment. Someone is at my door. Okay. My apologies for the interruption. I am back. So part C, explaining part C. So in part C, you are given a percent yield and you're told the reaction takes place at STP. There's 1 atmosphere and 273. That's all that's saying is that it's at STP. Okay. So you're going to use the 22.4 number. They're just saying the 22.4 number is valid. What you need to base part C off of is the mass amount in part B. Okay. So everything builds. So what part C is asking you, if you read part B, it says you make that amount of nitrogen dioxide at a 100% yield. What part C is saying is that if instead of a 100% yield, we instead drop that down to an 86% yield, how much oxygen would we need to still make 0.0065 grams of nitrogen? That's what part C is asking you. You want to make 0.0065 grams of nitrogen dioxide. You want to make that much. But you know you only get an 86% yield. So how much oxygen would you need if you only get an 86% yield? Okay. So that's what they're asking you for. That's what they want you to figure out. That's what part C is. Okay. And I believe that is it for today. I think I want to do one more example, but we're almost at the mark. I don't want to extend this too much. I'll do one more example. With the excess, how many grams of the excess will remain if we have this much and that much of, okay, so let's balance the equation first. So we want to make this. Okay, so to balance this needs to be a 2. This needs to be a 5. And then this needs to be 2. Okay, so now that it's balanced. Step 1, figure out which one is limiting. We have, it's 400 and that's 800. So we have 400 grams of nitrogen and 800 grams of oxygen. I'm going to skip through some steps just for the sake of time. So 400 grams, the molar mass of nitrogen is 28. Remember, for 1, it's 14, but you have 2 of them. So it should be 28. So we have 14.29 moles of nitrogen. And then 800 divided by 32 should be 25. We have 25 moles of oxygen. Okay. So then we got to divide this by 2 and divide that by 5. This is going to be 5. And then that is going to be 14.29 divided by 2. This is 7.145. So what I did here was I converted the grams to moles. I did that right away. Grams to moles. That's what I did for the first part. And then I'm dividing them by the coefficient to find out which one is limiting. That's what I just did it really fast. 5 is smaller than 7, so oxygen is limiting. Okay. So now we know oxygen is our limiting reactant. So now we need to base everything off of that. We want to know how much of the excess is going to be left over. Okay. So if we use 25, if we use up 25 moles of oxygen, how many moles of nitrogen do we need? So we have to convert that into moles of nitrogen. So we have 25 times, set up your ratio. Nitrogen should go up top. Oxygen should go on the bottom. Multiply that out. So 25 times 2 over 5 gives you 10. So we need 10 moles of nitrogen. We need 10 moles of nitrogen. We have 14.29 moles of nitrogen. So 14.29 minus 10 tells us that we will have 4.29 moles of nitrogen left over. Moles N2 left over. Okay. And now that we know how much of it we have left over, they want it in grams, so we need to convert this to grams. So then you just multiply it 4.29 by its molar mass, which in this case is 28. And if you do that, you get 120.1. Okay, so that should be A. Okay, that's it for today. Sorry for it getting a little lengthy, but there was a lot to talk about. Happy Wednesday. Hope you guys are doing okay. Again, for today, skip part E in number 1 and part D in number 2. I'll put it in the description to remind you, but that's it for today's lesson. Okay, take care, guys. Have a good one. Stay safe.